In this work, we present a methodology that uses an optical tactile sensor for efficient tactile exploration of embedded objects in soft materials. Different from other papers where tactile sensors are used to estimate the local presence of hard embedded objects in soft materials, we generate a probabilistic map of the locations of such objects using a Bayesian approach in a larger region. We use the probabilistic map to drive the exploration of the workspace and approximate the shape of the embedded objects, different from other papers where such shape reconstruction is done on rigid objects. Our method is able to detect and approximate the shapes of closely embedded and discontinuous objects within the soft material, independent of their continuity, relying solely on their spatial grouping within the workspace. Our proposed method is summarized in the following figure. There is an exploration phase, where a probabilistic estimate of the location of the embedded objects is built using a Bayesian approach. We first sample the workspace using DenseStack 2.0. The sensor from the raw image produces a depth image. This depth image is then processed by thresholding a minimum amount of deformation. The result is a series of clusters from which we can find their corresponding centroids. If deformation is present, we add the locations of the centroid with a label of 1 to the training data. If no information is observed after the thresholding, the center of the image is added to the training data with a label of 0. With the collected data, we train a Gaussian process for classification, which provides both the probability of presence as well as the measure of confidence of such prediction. We then choose an example by minimizing the uncertainty of the prediction and the discrepancy, which serves as a quantitative measure of coverage of the workspace. The entire process is repeated to choose an example. The exploration phase is then followed by a mapping phase, which exploits a probabilistic map to reconstruct the underlying topography of the workspace by sampling in more detailed regions where there is expected to be embedded objects. The mapping phase of the algorithm has a similar procedure to the exploration phase. However, the emphasis of this stage is to reconstruct the shape of the embedded objects. The overall cycle remains the same. However, in this case, the objective that we use to choose the next sample prioritizes the predicted presence of embedded objects rather than the reduction of uncertainty. With the collected depth data from DenseStack 2.0, we can then approximate the underlying topography by representing it as a point cloud. For the experimental validation of our method, we made a perforated acrylic bed where we can arrange a series of quartz beads in any desired configuration. The array is covered with a polyethylene foam that prevents direct observation of the configuration and requires the use of tactile exploration for shape reconstruction. Here we can see an example of the progression of the exploration phase. We can see how the probability of presence starts to resemble the actual configuration and how the uncertainty goes down as well. We evaluate the performance of our method against a fully random policy with 10 different configurations of the bits. As we can see, our method in red outperforms the random policy in green. Here we can see an example of the progression of the mapping phase. As seen in the video, with every sample we better approximate the actual configuration. Once again, we compare against the random policy for the 10-bit configurations, and the results show that our method is better capable of approximating the underlying topography. For more details, we invite you to consult the accompanying paper. We thank you for your attention.